Hey folks. So in this lecture I want to talk about conservation of energy and how we can include our potential energy terms now in our idea of conservation of energy. So far we've said conservation of energy means that we can't create or destroy energy, it just is, and that we can transform it. We can take it from one system, turn it into a different type of energy. But we cannot just create energy. There is an underlying kind of complementary conservation law to this, the conservation of mass, but I'll talk about that a little bit later. I want to get into isolated and non-isolated systems specifically. So for conservation of isolated systems, we're saying that the total mechanical energy is equal to 0. Or I should say, already putting some flubs in here. The change in total mechanical energy is equal to 0. The change is equal to 0 for isolated systems. All right, now let's refresh our definition of total mechanical energy. Mechanical energy is, we're going to say, is equal to all the push-pull kind of energies, right? Our kinetic energies and our potential energies. I'm going to write this, though, as delta E. The change in mechanical energy is going to be the change in kinetic energy plus the change in potential energies. All right. Now, you'll see me sometimes write Ke for kinetic energy. Sometimes I'll just write K. In both of those situations, as long as it's uppercase K, we should be pretty clear in understanding that it's going to be our kinetic energy. So for isolated systems, we have a total change in that mechanical energy of 0. For non-isolated systems, we're going to say that our total mechanical energy change is equal to the net work done by the environment. Right, which is actually kind of what we talked about a lot last week, right? This is our more general situation. So when we talk about isolated and non-isolated, what we're actually saying is it interacting with the environment, or is it completely isolated from its environment? Having a simple experiment or a simple, energy interaction out in deep space, it's probably going to be pretty isolated from anything else interacting with it. But if I'm thinking about it, maybe having a little toy matchbox car or something go down a ramp, it's actually going to interact with its environment quite a lot, right? There's a lot of factors that go into, is the track going to wobble? Is there friction on the track? Is it making sound? Is it heating up at all? Things like that are non-isolated systems, and so we can talk about the external work from our environment. So when we're saying this, what we're actually saying is that our change in kinetic energy plus our change in potential energy is equal to the work externally done by the environment. Now, that's a lot of deltas. We can actually break this apart a little bit and talk about, Kf minus Ki, and this is where I'm going to switch to Ks because writing Kei, Kef just gets a bit much. So Kf, Ki plus Uf minus Ui is equal to my work done externally. So a lot of times the way that we want to approach problems is what do I have initially? What work do I do by the environment? What do I end up with? All right, we can rewrite this expression as what we just said. What do I have initially? What kinetic energy do I have initially? What potential energy do I have initially? What work then am I going to do on this system? that gives me what kinetic energy I have at the end, plus the potential energy I have at the end. All right, so we have some initial, some environmental, or external. I'll say environment. And then we have some final. Right? What do I start with? What do I do? Right? Externally, not just talking about changing internal interactions, just changing the height or something like that. But what does friction maybe give or take out of the system? What does an applied force, me maybe pushing on a system, do to the kinetic energy or potential energy at the end? So at this point, so I'm going to actually move that. And I really, I took an arrowhead with me here. All right, that's okay. So where's that arrowhead? So this is a really good kind of starter equation to be thinking about when we're solving problems. So I really recommend that. Now, the only other thing I want to talk about in this lecture is this idea of an energy diagram. Energy diagrams are kind of helpful. The book likes to use them to visualize graphically how much energy is being transformed in a system, but also how it's all conserved. So the idea is that we have a ball. We have a ball being thrown up into the air. This is going to be a very simple example that we use over and over and over again. But I have a ball sent up into the air. My potential energy, we're going to say, is 0 at the ground. We'll talk about that in maybe the next episode, next lecture. I gotta figure out the organization of my notes here, but we're going to talk about the relativity of potential energy in a second. So when I think about this system, let's take it frame by frame by frame. I have something where I have a lot of velocity going up. I have a little velocity in the middle. I have no velocity at the top, and then a little velocity going down, and then a lot of velocity at the end. So in this first time frame, I have a whole lot. Actually, let's change this just up a little bit so that way it's pretty clear. I have a lot of kinetic energy and very, very little potential energy. So maybe let's go all the way to here, and then we can, let's do green. I like green. Just say, boop, we got a little bit of potential energy because we're not right at the ground. In our second scenario here, I have a lot more potential energy, and I have a lot less kinetic energy. So we're going to say that they're roughly equal, right? We're making column graphs, bar graphs here, right? At the top, I have roughly 0 kinetic energy. I only have potential energy. And so I'm going to say that it's only like this. Then I start to reverse it, and I go back down. When I go back down, I'm trading my potential energy for kinetic energy, right? Over here, I traded kinetic energy for potential energy. I stored that kinetic energy in in height, right? In this interaction with the Earth. I stored it all, and then I had to get it back, right? I've deposited it over here. Now I'm withdrawing it over here, and I'm back down to almost full kinetic energy with just a smidge of potential. All right. So this starts to show us how we have this back and forth, this seesawing motion of conservation of energy. Notice that the total amount of energy is pretty much constant the entire time here. We've just traded hands. Which hand is the energy actually in? Is it in potential? Is it in kinetic? Well, it depends on where we are in our path. But the total energy of our system, the total mechanical energy of our system, is staying constant here. All right, so that's energy diagrams in a nutshell. I think I have a homework problem on it, so I wanted to make sure I prep everyone for it. But that's also isolated and non-isolated systems and energy conservation in a nutshell. If you have questions, feel free to email me or swing into an office hour this week. I want to make sure that people feel a little bit comfortable about this before the exam next week. And again, potential energy is now a different way of talking about a lot of things that we attribute it to work, right? We've talked about the energy, the work that gravity did on an object going up into the air, and then it did another amount of work as it fell back down. When I say that I took energy out of my system, put it into the environment, and then when I let it fall back down, I take that energy from the environment and put it back into my system, it sounds like I'm storing something, right? It sounds like I'm storing it in some sort of interaction, and I am. So this is a little bit more natural of a way of talking about energy, specifically this interaction energy. So that's this lecture. It's long enough as it is. Have a good one, and I'll see you back here in just a bit.